So last thing in the chemistry unit is the mole concept and the mole equation. All right, so in most forms of measurement, okay, we use things like volume, like liters, okay, or we use mass, grams, kilograms, okay, or we use like length, centimeters, meters, things like that, okay. In chemistry, we can use those, okay, we can use liters, we can use volume, we can use mass and kilograms or grams, but in chemistry, we need a little bit more than that. We need to be able to talk about the number of particles that might be involved in a reaction. Are particles, are atoms small? Is it possible to count the number of atoms I might have in a chemical reaction? No. Even if I'm dealing with the incredibly small amounts that we would have used in our first lab, it would take me the rest of my life to count the number of atoms in one of those small samples. Okay, they're tiny. And so there's no way for me to really do that. So what we need is a number that can represent, or a unit, sorry, that can represent a large number of particles and have it be kind of standard. All right. Bakers use a number like this all the time. When you buy donuts, you usually buy them in dozens. How many in a dozen? 12. Okay, it's a standardized number. If someone says a dozen, they know that you mean 12. Okay, you buy a dozen eggs, there's 12 of those. Right? We know that that's what that number represents. In chemistry, we have a similar number, and it's called the mole. Okay, the mole is a representative number that was arrived at through a lot of experimentation. Okay, and that's what we're going to talk about today: is what is the mole? How much does it represent? How does it work? Okay, so the mole is a unit for measuring the number of particles. Okay, the relationship, we need to understand the relationship between moles, mass, so the amount of something, and molar mass. Molar mass is the mass of 1 mole. Okay, just so that we're clear on that. Okay, molar mass is the mass in grams of 1 mole. Okay, and then we're going to use the mole equation to solve problems. Now the mole equation looks like this, guys. N equals little m over big M. Okay, it's like one of the worst equations ever devised. Okay, there are 26 letters in the English alphabet, and we used M twice in a 3-variable formula. Right, that's how chemists think, I guess. I don't know. All right, so N stands for the number of moles. Little m stands for mass, and that'll be in grams. And this is molar mass. And that's in grams per mole because it's the mass of 1 mole. Okay? N, like we said, is the number of moles. All right, so we'll be using that formula, which means we'll have to do a little bit of algebra. That is manipulating equations. Don't worry, that's easy. I don't know why people think it's hard. They've been told for some reason that manipulating equations is hard. I'm going to show you it's not. Okay. All right. So when we're talking about a reaction, we generally use grams, mass, or moles to denote how much of something is in the reaction. Very rarely do we use volume. We would only do that if the things reacting were both gases. Okay, so most of the time it's going to be grams, mass, or moles. Okay. Now, for the idea of the mole, okay, what scientists did, okay, is that they took the simplest element. What's the simplest element? Hydrogen. Okay, they took hydrogen gas and they got 1 gram of it, and then they tried to figure out how many particles are in 1 gram of hydrogen gas. Okay, how do you suppose they figured out how many particles were in that 1 gram? Because it would have been impossible to count. Not even an educated guess. At the time they were doing this, they knew that protons existed and electrons existed and neutrons existed. Okay, and they had a pretty good idea of the mass of each of those particles. Because hydrogen is such a simple atom, it wasn't too hard to calculate how many hydrogen atoms there were in that 1 gram of hydrogen gas, okay? Based on the fact that a hydrogen atom has 1 proton and 1 1 electron. Okay, so it wasn't hard to figure out how many particles there were in that 1 gram of hydrogen gas. And what they found was that there were this many. 6.02 times 10 to the 23. That's 602 with 21 zeros behind it. It is an unfathomably large number. Okay, huge. Like I said, it would take you the rest of your life and probably your next few lives to count that many, right? Because the worst part of that would be you'd probably lose count a couple of times. All right, so you're, like 758 billion, 295 million, oh crap, 1, 2, right? Like you wouldn't want to lose count. Okay, so we got a huge number here. Okay, but that number represents 1 mole. For hydrogen, the mass of that many particles is just over 1 gram. If you look on your periodic table, okay, if everyone can take that out, you'll see in the box for hydrogen, its molar mass. Okay? Its molar mass is in the top right-hand corner of its square, 1.01 grams per mole. Okay, now we said when they were doing this experiment, they had what they thought was 1 gram of hydrogen gas. Now, since then, we've become more accurate in our calculations of what particle masses and stuff like that are, so the number's been revised. Okay, but if I have that many atoms of hydrogen, it will have a mass of 1 gram, 1.01 grams. Okay, everybody with me there? If I have that many, 6.02 times 10 to the 23 atoms of sodium, it'll have a mass of 22.99 grams. Okay, so on all of our elements here, the atomic mass is, or the molar mass, is that number in the top right-hand corner. Okay, that tells you the mass of 1 mole of that material. Okay, so why is it different for every element? So, yeah, here's. Right. Okay. No 2 elements have atoms that are alike, right? Hydrogen is very simple, 1 proton, 1 electron. Okay, but if I get down to sodium, okay, it's got 11 protons, it's got 12 neutrons, it's got 11 electrons. There's just more to it. So its atoms are heavier and bigger. So thus, if I have the same number of sodium atoms as I have hydrogen atoms, I would have obviously more mass. Everybody okay with that? All right. Okay, so this number, you're not going to have to memorize it, okay, but it's a number that we're going to use a lot, okay. I will put it on the unit exam, okay. It's known as Avogadro's number because Avogadro is the main scientist who was responsible for discovering it, okay. He's the guy who did that whole thing with the hydrogen atoms, okay, discovering how many there were in that 1 gram. All right, so it's going to be an important number for us to use, okay, and it works just like 12 represents a dozen. That number always represents a mole. If I have 1 mole of anything, hydrogen, gold, lead, uranium, whatever, if I have 1 mole of that, that is how many atoms I have. Okay, everybody with me there? All right. Okay, because it's the same for a dozen, right? If I have a dozen donuts, I have 12 donuts. If I have a dozen eggs, I have 12 eggs. A dozen is always 12. A mole is always that many. Okay. All right. So the mass of 1 mole of a substance is known as that substance's molar mass. Now, obviously, it's pretty easy for atoms because it's listed there on the periodic table. What if I want to calculate the molar mass of a compound? I have to add them up, exactly. Okay, so if I'm looking at water, for example, okay, water is H2O. 2 hydrogens, 1 oxygen. Right? So if I want to find the molar mass of that, I take the molar mass of hydrogen, 1.01. How many hydrogens are there? Multiply it by 2. And add that to the molar mass of oxygen, 16. Okay? So I find out that the molar mass of water is 18.02 grams per mole. That means if I have 6.02 times 10 to the 23 water molecules, it will have a mass of 18 grams. Now, to give you an idea of just how little water that is, that would fit in the cap of a water bottle. Okay, 18 milliliters is not very much. Okay, because 1 milliliter of water is 1 gram. Okay, so not very much. But there would be 6.02 times 10 to the 23 molecules of water in that amount. Okay, all right. Is that a fairly easy calculation to make? Okay. Then I want you guys to try and calculate the molar mass of, let's just say 1 and 2 for right now. Okay, so you're going to use your periodic table and calculate the molar mass of those two compounds. Okay, let's have a look at the first one here. So I've got sodium chloride, okay? How many of each? Just one, okay? So there's one sodium atom, so I'm going to go 22.99 because that's the molar mass of sodium, and then plus 35.45, which is the molar mass of chlorine, okay? And I'm just going to add those two together. So 22.99 plus 35.45, right, gives me 58.44 grams per mole. Okay, so that's about as easy as they get when they're both a 1. Right, I just have to look up the numbers and add them together. Okay, for the second one here, I got iron 3 bromide. Okay, so I've got 1 iron, okay, which is what, 55.85? Yeah, okay. So I got 55.85, that's my 1 iron. And then I have, how many bromines? 3. Okay, so I've got to go 79.9? Yeah. Times 3. Okay, so I'm going to have 55.85 plus 79.9 times 3. All right, so that's going to be 295.55 grams per mole. Okay, how important are units? Very. If we don't put units on an answer, it's wrong. Okay, because then I don't know whether you said it was 295.55 grams per mole, 295.55 meters, old ladies with walkers, I don't know. Okay, you have to tell me what it is you measured by putting units on there. Very common mistake to forget units. All right, I want you guys to try the rest of these, and then we'll go over them here in a minute. All right, so for number 3, how many phosphorus atoms do we have? 2. All right, so phosphorus is 30.97, right? Okay, so we've got 30.97 times 2, okay, and then we have how many oxygens? 5. All right, so we're going to add that to 16 times 5. Okay, so we're looking at 30.97 times 2 plus 16 times 5. All right, so 141.94 grams per mole for our molar mass of diphosphorus pentaoxide. Okay. All right, how many people have done number 4? Okay, do we need more time on number 4, or are we just stuck on 4? I'll give you another minute, then we'll go over. Okay, so when we get compounds that have polyatomic ions and brackets and things like that, we have to be really careful about tracking how much of everything there is. Okay, so in this compound, ammonium sulfate, how many nitrogen atoms are there? 2. Okay, I don't have a molar mass for ammonium. I have to do this element by element. Okay, and because of these brackets and the 2 outside of them, it says there are 2 ammonium ions. Right, that means there's 2 nitrogens and how many hydrogens? 8. Okay, this 2 means multiply everything in the brackets by 2. Right, so I'm going to have 14.01, that's the nitrogen, times 2, plus 1.01 times 8, that's the 8 hydrogens. Okay, I've got 1 sulfur, so that's 32.08, 07. Okay, and I've got 4 oxygens. Okay, so 16 times 4, right? So the brackets, you really have to keep track of everything, and you have to do this again, element by element. All right, so we're going to have 28.02, that's the nitrogens, plus 8.08, that's the hydrogens, plus 32.07, that's the sulfur, plus 16 times 4. All right, so we're looking at 132.17 grams per mole. And then times it by 2, that'll work too, either way. Yeah, so if you found them, yeah, so if you found the molar mass of the whole ion and then multiplied it by 2, yeah, same idea. Yeah, math's the same. So, all right, how many people have done number 5? All right, let's have a look at that one too. So we got scandium carbonate here. Okay, so scandium is 44.96. Is that what it is on yours? Okay, because sometimes the numbers on yours are different. 44.96, and there's how many of them? 2. All right, so we're going to multiply that by 2, plus how many carbons? 3. Okay, so I'm going to have 12.01 times 3, and I've got how many oxygens? 9. All right, so we got 44.96 times 2 plus 12.01 times 3 plus 16 times 9. 269.95 grams per mole. Okay, so that's kind of one of our fundamental skills involved with doing mole calculations, is being able to calculate the molar mass. Okay, the reason we need to be able to calculate the molar mass is, as we learned before, it is part of this equation. Okay, it is big M. All right, so we'll always have big M as long as we have a periodic table. Right, we'll always be able to calculate what big M is, okay, to use in this equation. Right, and that's how we get it. Okay, any questions on how that works? No? All right, when we're interpreting a chemical reaction, so if we have a balanced chemical reaction like we do right here, okay, there's a couple of different ways we can look at it. We can interpret it literally, and we can say, in this reaction, 1 molecule of nitrogen gas is reacting with 3 molecules of hydrogen gas to form 2 molecules of ammonia, of nitrogen trihydride. Realistically, would I even notice that reaction occurs? If it's 1 molecule reacts with 3 molecules, makes 2 molecules? No. Okay, we're talking an incredibly small amount of stuff. So we very rarely ever interpret a reaction to mean that. Okay, what we more often mean is that I have 1 mole of nitrogen reacting with 3 moles of hydrogen to produce 2 moles of nitrogen trihydride. Okay, is that a reaction I would notice? Yeah, because now I'm talking about considerably larger amounts of everything. Okay, I'm talking about 6.02 times 10 to the 23 molecules of this stuff. And I'm talking about 3 times that many molecules of this stuff. Okay, producing 2 moles of nitrogen trihydride. Okay, that's a lot more stuff. Okay. So these coefficients, guys, are just a ratio, okay? This could be like 10 to 30 to 20, okay? It could be 100 to 300 to 200, okay? It's still balanced. It's all about the ratios of everything in the reaction, okay? All right, so like we said here, one way we can interpret it is literally. The number of particles is the true number. We'd never notice a reaction that small, so we very rarely interpret it that way, okay? Oh, this is Avogadro, by the way. It kind of looks like a mole. Yeah, yeah, avocado's number. Yeah, okay. He kind of looks like a mole though. He's kind of got those like weird big eyes, really small neck and shoulders for digging holes in underground tunnels. I don't know. I don't know why he decided the mole was the unit he should have. I think it's because he looked like a mole. That's probably his nickname, a mole. right? Okay. The second thing here is we could interpret it as meaning moles. 1 mole of nitrogen, 3 moles of hydrogen produces 2 moles of nitrogen trihydride. That is the most common way that we interpret a chemical reaction. And that comes into play in Chem 20 almost right away. Okay? In Chem 20, one of the first things you will do is what we call reaction stoichiometry. Okay? And what that means is we use the mass of reactants along with moles to calculate how much in grams of something we'll produce, right? This is important because if you're doing something industrially, you need to know from the ingredients or from your products, if you need to produce this much stuff, like 100 kilograms of it, how much of everything else do I need? Okay, obviously, if I'm going to have 100 grams of or 100 kilograms of product, I'm going to need 100 kilograms of reactants. But how much of that is nitrogen? How much of it is hydrogen? How many kilograms of each one do I need? Okay, and so being able to do these mole calculations allows me to do that. Okay, to break down a reaction into how much of this stuff, how much of that stuff. Okay, and that's the first thing you do in Chem 20. We don't do it in Science 10. Okay, but you do it right away in Chem 20. All right, so that's the most important information that a chemical reaction provides. The coefficients, okay, those numbers we put in when we're balancing, tell us the relative number of moles of reactants and products in a chemical reaction. And from that amount, the masses of reactants and products can be calculated. That's reaction stoichiometry. All right, it could also mean mass, okay? And if it means mass, the ratios are not like literal, or they're not exactly like they are there, okay? So that would be, if I had 1 mole of nitrogen, I would have 28 grams of it, okay? If I had 3 moles of hydrogen gas, okay, I would have 6 grams there, okay, for a total of 34 grams of reactants, which means I'd have 34 grams of products, okay? So it can work that way as well. All right, looking at the mole equation. Algebra. I know that somewhere along the way, some well-meaning, good-hearted person told you that to manipulate an equation like this, you draw one of these. That person lied. Okay, they meant well, but they're wrong. You do not use a triangle to manipulate an equation. Because that's like saying, you hurt your pinky toe, here's a crutch, use it for the rest of your life. It's just dumb. You don't need a triangle to manipulate an equation. Okay? You can do math. You can do algebra. Everybody can do it. Okay? I'm a prime example. Guys, I was one of the worst math students. Okay? And I teach physics. And all physics is, the math of physics is manipulating equations, performing algebra. Okay? And I can do that. There's 3 simple rules to being able to manipulate equations and perform algebra reliably every single time. Okay? You don't have to be great at math to be able to manipulate an equation to solve for something. Okay? So I don't want to see triangles because you don't need them. Second reason I don't want to see triangles, I teach physics, and triangles stop working right away because triangles only work if the equation is set up the right way and only has 3 variables in it. Okay? For example, here's a formula that you might use, or you will use, in Physics 20. Got a triangle that'll work for that? Not even a trapezoid or a rhombus. Okay? It's just not going to work. You can't use a triangle for everything. And so it's a crutch that someone will cruelly kick out from underneath you and make you fall flat on your face. Okay? Don't use a triangle. Okay? It's just not going to work. Okay? So here's what we need to know about algebra. Okay? The 3 simple rules of algebra, and I want you to write these down. Okay? The first rule of algebra is this. Okay, rule number one of algebra is, if you want to move a variable, you do that by performing the opposite operation. So, in this equation right now, I am dividing by big M. If I want to move big M over to the other side of the reaction, or sorry, of the equation, what do I do? Right, times big M. Here comes the second rule. Okay, the second rule always happens right after the first rule. Whatever you do to one side of the equation, you must do to the other. It's the golden rule of algebra. Okay, so really what we're saying here, guys, is this. I have little m over big M. If I want to get little m by itself, I have to move big M over to the other side. Right now, I'm dividing by big M. So I want to do the opposite in order to move it. That means I multiply by big M. When I do that, I have big M divided by big M, which equals 1. So it cancels. All right, now big M is gone from that side of the equation. But what I do to one side, I must do to the other. Now I moved big M over to the other side. Okay? And that was all I had to do. For this equation, you actually only need the first two rules of algebra. Okay? Because it's a simple equation. Right? The third rule involves when you have more than three things. Okay? So the third rule, just so you have it, is this. Move what's not attached to what you're looking for first. Okay, so what I mean by that rule, guys, is this. Let's say I have this equation here. Okay, this is the graphing equation. If you've taken Math 10, you've already seen this equation. Y equals m times x plus b. If I want to solve for m, I need to move x and b over to this side of the equation. Agreed? Okay, that's how I would isolate m. And that's what we want to do, is isolate m. All right, so the third rule of algebra applies to an equation like this. Right now, what's not attached to m? Okay, y isn't, but y is already over on the other side. B. B is not attached to m because there's x is. X is right beside it. It's attached to it. Okay, b is not attached to it. So I'm going to move b over to the other side. How am I going to move b? I'm going to subtract it. I'm going to do the opposite operation. So I'll subtract b from this side, which will make it cancel. And then what I do to one side, I have to do to the other. So now I have y minus b equals m times x. Okay, I want m by itself. What do I do with x? I divide it, because right now I'm multiplying m by it. If I want to move something, I do the opposite. I just isolated m. And all I had to do was follow three simple rules. Okay. Should algebra be scary? Algebra is not hard. Okay, you just have to remember 3 rules. Guys, those 3 rules got me through university physics. And I don't mean to brag, but I got 100% university physics. And I'm not that good at math. Okay, and I hate saying that because it feeds the stereotype that math is hard. Okay, I just don't really have a strong mathematical mind, but I can manipulate equations like anybody. Okay, put me up against the best algebra guys. I can manipulate an equation. Don't ask me about differential calculus. I don't get that. All right, it's crazy. The only way I got through calculus was to memorize the examples in the textbook and write them down on my final exam and get part marks for method. Luckily, I was in a class full of even dumber people, okay? And it was graded on the curve. So it didn't matter whether you passed or failed as long as you did better than half of the people in the class you passed. Okay? Yeah. All right. But manipulating equations, follow 3 rules. You can't go wrong. Okay? Can't go wrong. All right. So let's look at this for manipulation purposes. Obviously, if I'm solving for n, it's already set up. I don't have to move anything. Agreed? Okay, so as long as I'm given mass in grams and the compound itself, I can calculate the molar mass, then I can do this calculation. Right? If I want to solve for m using this equation, then I multiply both sides by big M. That's all. That's the only manipulation of that equation you're ever going to have to do. Why won't we ever have to solve for big M using this equation? Because you have it, right? You'll always use the periodic table to get it. It's not, you're never going to have to use the mole equation to solve for big M. Okay, that's the only manipulation of that equation you're ever going to have to do. Okay, you're either going to solve for n or you're going to solve for little m. Okay, and that's it. All right, so nothing to be intimidated by. All right. So this is an example of the simplest mole equation calculation we can have. So we'll do this one and then we'll call it a day. Okay, so I want you to write this one down, okay, because I don't think it's in your notes. All right, we want to calculate how many moles of calcium chloride are in 90 grams. Okay, so remembering that the mole equation looks like this, n equals little m over big M. N is the number of moles. So that's what I'm looking for, okay, because they want to know how many moles. Right? So whenever we're doing a problem-solving problem in science, okay, we always want to write down our givens. That is, what numbers did the question give us? Right? So it didn't give me n because it wants me to find that. So I always write n equals a question mark. Okay, did they give me little m? Yeah, 90 grams, right? Little m is mass in grams, so the 90 grams is little m. Okay, and did they give me at least a way to calculate big M? They did, because they told me it's calcium chloride. So all I have to do is put in my numbers. So 40.08, that's my 1 calcium, plus 35.45, okay, that's my chlorine. That should be 110.98 grams per mole, I think. I probably shouldn't do that in my head because I just said I wasn't really good at that, but I think that's what it comes out to. Yeah, 70.9, yes, 110.98. Okay, so I have M and I have big M. Can I finish this calculation off? Yeah, this is why we write down our givens. Okay, when we get into the physics part of this course, you'll have a whole sheet full of formulas. And you'll have to decide from your givens which formula you're supposed to use for that question. So I always actually give people a mark for doing just this. Listing what the question gave. That's worth a mark. Okay. Then you would get a mark for choosing the correct formula. In this case, it's obvious there's only one formula to use. Okay. And if you had to manipulate it, I would give you another mark for that. All right. We'll talk more about that on Monday.